Okay, today's experiment is about Beer's law. It will be recorded and then I'll upload it inside iCollege. So Beer's law, because I look at the the whole thing here. It's not really very adequate explanation of in the previous video. I mean, there is details, but let's put. I will combine both videos together. So Beer's law, it's about a color solution. A color solution can absorb light, and then from this absorbance we can determine the concentration of this solution from this absorbance. One can determine the concentration of this solution. So transferring into a mathematical formula, A is absorbance equal a constant called absorptivity, molar absorptivity, multiplied by the length of the cell itself, the light pathway. That's the length multiplied by the concentration. So let's do this. This is absorbance. Okay, this is molar absorptivity. I think it's absorbance with a P. So absorptivity. This is light pathway, length of the pathway here, length of light, and this is the concentration. So really what we are interested in the fact that this law here is telling us that the absorbance of a color solution is direct proportional to its concentration. The higher the concentration of the solution, the color solution. It does not work for non-color solution. So if I want to measure the concentration of H2O, I cannot by this method, by Beer's law. Beer's law is required. You have to have, this is a must. So this is a requirement. Without it, you cannot determine anything. This is a requirement. You have to have a color solution. This color solution will be able to absorb light, correct? And this light, this absorbance always direct proportional to its concentration. Now, saying this, let's look at the picture here. Can I take this one out? Everybody has it? Everybody has it? This is in the other video, the same thing, but I just want to explain this one quickly, so then we can go to the. So what you will see here, you will see if this is the cuvette here, you will have today to work with something called cuvette. This is called a cuvette. It's a special cell, and the light will go in from this side, okay, and go from outside. So this is light intensity in, light intensity out. And the transmittance in percentage here is really the ratio between out to in. Light intensity in and light intensity out. That's what's really transmittance. Okay, and the transmittance is related to absorbance in a formula, correct? In a formula. So transmittance is absorbance 2 minus transmittance. So, but this is the whole ratio here. Transmittance related to the absorbance, and the absorbance is, and the absorbance here is related to the concentration, which is really, we are looking for this. We are looking at the concentration of unknown solution, color solution. That's what we are looking for the experiment. This is unknown. We'll have an unknown colored solution, and we have to determine its concentration. That's the whole thing here. That's the concentration here. Correct, guys? So this is just the whole idea of this. There is another video that tells you the whole details. So this is the whole idea about the experiment. So the experiment today, you will be able to determine the concentration of the unknown solution using its ability to absorb light. This solution has to be colored, and therefore you will use the spectrophotometer all over the places. Here it takes about 20-15 minutes to warm up, so we'll be able to do it. So can I take this one out? So here it is. Now we will, the spectrophotometer has to be calibrated. It's not working like normal way you put something on the balance and you weigh the whole mass. No, it has to be first calibrated before you are working on it. So the first thing here we have to calibrate, we'll be using what? Distilled H2O. Why we are using distilled H2O? The transmittance of the light of H2O, if we have the cuvette again here, and we put this one inside the so the light will go in, correct? Light will go out, and the transmittance here, because this is H2O, is not absorbing. So the absorbance will be what? Absorbance will be 0. No absorbance. Every in and out will be equal. In equal out. Equal 100% of light intensity. 100% of light intensity going in and going out. So we'll be using this one here as a reference, as a blank. Why as a reference? Because we want to calibrate, or for calibration. This whole setup here, just we want to calibrate the spectrophotometer. So we have to tell the spectrophotometer where it will start. It will start from 0. Are you following me here? It has to be told, the spectrophotometer. If you are on it now like this, measuring your solution, you will not get a good data because you did not tell, you did not calibrate, you did not tell the digital software from where you start. We started with intensity is equal going in, going out. H2O is not absorbing any light. You can get the light might be reflected or deflected or reflected, but it's not absorbing. H2O is not absorbing light. But color solution, they do absorb. So, and that's we have to do the first calibration for the spectrophotometer. This calibration here for the spectrophotometer. Anytime I measure the absorbance of a color solution, I use the word spectrophotometer. The old times we used 20, spectrophotometer 20, I'll show you here. Can I take this one out? That's a very bulky instrument we don't use now anymore. This is a very fancy, small, tiny one, rather than the old one. So 20, 30 years ago we were using, even here a couple, 10 years ago we were using the bulky one, which is still good, but it's more mechanical. Does not have any digital software. So everything you have to do it per hand. So can I take this one out? I'm taking this one out, showing you in this. You can see let me go and show you the picture of the spectrophotometer. That's maybe not here, maybe in the introduction. Well, it should be here, but just bear with me. It's a very bulky, heavy equipment, and it is mechanical. It's not here. This one here, this is called spectrophotometer 20, but then abbreviated as spec instead of spectrophotometer. That's long word, spec 20. So the word is spec 20 means spectrophotometer. It's not working with the computer. Does not have any way of digital setup. Everything you can see just like a balance. You can see whatever the numbers here, and then you all those knobs you control the wavelength and read the absorbance from there. Okay, guys. So it's not a fancy one, but it's working for us. So now we are replacing this one here with the fancy one, which is called Vernier Spectrovis or Spectrovis Plus. That's the small one you have. But the good idea is, the main idea is both of them is not working when they are cold. You have to at least 15 to 20 minutes let them warm up. Whether you use the classical older one or the new one, you have to warm up, because you need the light will go through at the specific type of temperature. So, and it takes time to have the temperature stabilized, correct? So the room temperature. So what will happen here, we have a cuvette. We will make a solutions, we'll make a calibration curve. To know this solution, we have to make a calibration curve. So let me go here back. This is our vernier, and the light, you have a cuvette. The cuvette has two faces. When the light goes in, that's the transparent face. Transparent face of the cuvette. This called cuvette is made of glass, correct? And this is the transparent. So the light will go in and will go out, correct? This side here, the other side here in front of you here, this is and in the back as well. This is the harsh or the hard, they call it hard surface. So anytime you wanna touch this one here, you don't touch it with your finger, you don't touch this side. Here it is. This one, do not touch. Do not touch with your fingers. Somebody will tell me why? Because if you have a fingerprinting, if from your fingerprint any dirt, and this dirt has a color, will absorb what? Light. Or will be acting, if it's not absorbing, will be deflecting light off. So you'll not get a good reading of the intensity of the light coming out. So make sure whenever you have to, the face with the heart, it has the grooves here. So it's telling you to use those from this side. Every time you wanna grab this cuvette from this side, not from this side. This side the light will go through. And the light, as you can see, goes here. And the light will goes here and then will be detected in this side. See the arrow here? So the arrow where the transparent face of this cuvette. It's a pure glass. Nothing grooves, nothing like this. So you let the light go in, light go out. And then from the program there you can calibrate the whole thing first with H2O. Okay, and then we'll do the dilution solution. So we'll make a curve. So then after you are doing the blank, we have to do the curve. So calibration curve. So how we do the calibration curve? Well, it turns out to be, you will have nickel nickel complex compound. So we'll have today nickel, whoops, sorry. You'll have a compound, nickel complex compound, and you'll have cobalt. We'll not use the cobalt. We'll use just one of them, not both. We'll use one of them. So the nickel then we'll have to prepare out of this nickel 0.4 molar, and then we'll make dilutions. We'll make 4 dilutions. We'll make how many? 4 dilutions of this 0.4. First we'll prepare 0.4. We know the structure of this compound. We know its molar mass, correct? So we can determine, and we know how much we have. We'll use a volumetric flask. Here it is. So that's 100 ml volumetric flask. We'll determine the, and then make the molarity 0.4. Now, this details here is given to you in the solution. Can I take this one out? So let me maybe take this one. Everybody has this? Everybody has this? So let's take this one out and look at the nickel hexa aqua nitrate or chloride, either or, but we have to know exactly what we are using. So here it is. So the one we will be using is the nickel, not the cobalt. So here it is, nickel nitrate hexahydrate. Nickel nitrate hexahydrate is a complex compound. So nickel nitrate hexahydrate, we will use we'll have to prepare 0.4 molar. So how we do this? We'll not do this. This one will not do the cobalt. We'll do just not both. One or the other. We'll do the nickel, correct? So most of the cobalt look pinky color, and most of the nickel compounds look greenish. So that's general said. The greenish colors that's typical for nickel, and the purple color or pinky color is typical for cobalt compound. So we'll take this one here, and we have to know the molecular mass of this. I will need to prepare 0.4 molar. So I start whatever I have to begin with. That's the molarity here of this compound. Mole per liter is given to me. Mole per liter, that's the molarity here. Now, I need to get how many grams in 100 ml. We have to prepare everything in 100 ml, correct? This is a 100 ml volumetric flask. You have to use your 100 milliliter volumetric flask. This 100 ml is 0.1 liter, correct? Or if you want to sig fix, that's 0.1 00 liter, correct? So now I have this one here, mole per liter. So I multiply this one by 0.1 liter, correct? You can add to 0.3 sig fix. So liter with liter cancels out. Liter, if you look here, liter with liter cancels out. So that's the main thing, is you got rid of the liters here. Mole per liter multiplied by 0.1 liter, liter with liter cancels out. But I need the molar mass of this compound. I have to calculate the molar mass of compound. So I have to look up nickel, what's the atomic mass of it? Oxygen, what's the atomic mass of it? I have 2 multiplied by 3, I have 6 oxygens, correct? And I have the H2O is 18, by the way, 18. H2O, the whole thing is 18 multiplied by 6. So this is 18 multiplied by 6. Why is 18? Oxygen is 16 and hydrogen is 2. 2 multiply. Always remember the molar mass of some compounds, easy to memorize. Just for the fact, H2O is always 18 gram per mole, the molar mass of it. So 6 multiplied by 18, that's the molar mass of H2O. And then you have 6 oxygen, and you have 2 nitrogens. So add this plus this amount of H2O, that will give you the molar mass. The molar mass is already given to you. That's the molar mass, gram per mole. So the mole here with the mole here cancels out. So what's really left is number of grams, and it is what is calculated that for you, 7.3 grams. 7.3 grams. Okay, guys. So 7.3 grams. So you will weigh 7.3 grams here of this compound here, of the nickel nitrate hexahydrate. So when you add here, you have to add 100 mL, but you will never add 100 mL at once. You will add a couple milliliter distilled HOS 10, 15. You don't have to count. The main thing is, as you add, shake, keep shaking until you end up to everything is dissolved. Then you can fill all the way with distilled H2O to the line here. Then you have a solution which is 7.3 grams of your complex dissolved in 100 milliliter distilled H2O. And that will then count for your stock solution. This is my stock solution. Okay, this is my stock solution. Always stock solution is the highest concentration. This is my highest concentration of all the concentration I will make. Correct? So that's the first how to do the stock solution, to prepare stock solution. Any question about this? Any question about this? So you have the stock solution. You prepared your stock solution, 7.3 grams of the complex here. This is a complex. Every time you have a hydrate, this compound called a complex, because H2O is sitting sometimes in the top of the nickel nitrate. So it's a complex structure of the compound. It's ionic compound, but still complex ionic compound. So I have prepared now this 100 ml. Now I have to prepare the dilution of the 0.4. So can I take some out? Now I'll come here. I will make what dilutions? The Beer's law. If you recall, just to let you know, the Beer's law has a small tiny glitch that's not inside. That's not inside your procedure, but it has tiny glitch. The glitch here I'll show you. That's, you can get it from some textbook. They talk about this glitch, but you get it from the experience when you work with the color solution, measuring their concentration. We said absorbance is direct proportional to the concentration, correct? So when I have, and this is A constant, correct, multiplied by the concentration. A then turns to be the molar absorptivity, correct? The molar absorptivity of what? Of the glass you are using, of the material, the glass, the light will go through this material. That's the constant of it. What type of glass you are using, how many silica you are using, that's the constant here. That will be given to us, or we can calculate it from the calculation there. Multiplied by the light path going to the cell. Here it is, that's the light path here, guys. From here to here, that's the length of this cell, or cuvette, or cell. That's L. Here, this is L here. And the material here of this compound here, that will give you epsilon. Okay? And then multiply by the concentration with which you are in. So now the glitch here is you are expecting is, when you plot this one here with Excel, A multiplied by C goes from the origin here, and you think that you are getting what? You are getting a very nice, from the origin here, very nice linear. That's true. Now if you go too much of the concentration, then Beer's law will be broken. Then you will not get that. This will come what? It will come acting like, see here now? Watch it. No more linear relationship. It will come to type of like saturation. It will stop. So Beer's law works only for diluted solution. Make sure that you understand this. Only diluted solution only. Now if somebody will tell you take not 0.4 molar, take 3, 4, 5 molar, maybe I put this one here in multiple choice. Can I measure 5 molar solution with the spectrophotometer with Pierce law? The answer is no. If I have 4 molar or 5 molar, I'm not getting this. I'll be getting like something looking like this. Not a linear relationship. It's a curve. It's a curved thing. So it's not. Pierce law works only for diluted solution. That's the reason we are going to make some dilutions out of this 0.4. This is still not concentrated, but still a very good concentration. So we'll go lower than this. We'll go lower than this. Can I take this one out? Take this one out. Let's take this one out, and let's look at the dilutions. Now you'll take from your flask. Remember, you'll take from your flask. Remember the volumetric flask here. Just to recall them. Here yours. Here it is, your volumetric flask, guys, and you dissolved 7 gram of this complex nickel nitrate hexahydrate in 100 ml. This is 100 ml volumetric flask, H2O, correct? H2O is your solvent. And then what will happen here, you will take a graduate cylinder. You will have 4 test tubes. 1, 2, 3, 4 test tubes. You can label them. This is 1, this is 2, this is 3, this is 4. For the first one, you will take out of this using graduated cylinder here. Graduate cylinder here. So you use graduate cylinder here. Okay, guys? So you use the first one is you take 2 mL out of this. So 2 mL. Out of this, you will take the other one is 4 mL. 2 mL at the time. So 4 mL. Then the third one is 6 mL. The fourth one is using the graduate cylinder, guys. Using the graduate cylinder. But you will not put them inside first. I'm sorry, you will not put them. So what you will do here, you take for the first one here, let me just, here you take the 2 mL, correct? And now you have 2 mL here, for example, the first one. 2 mL, correct? You will add up to 10 mL. Up to 10 mL distilled H2O. Correct, yeah? Distilled H2O. So how many H2O you will add? Here 8 to make 10. How many in the second one? You took 4 mL of this flask, measured the graduate cylinder, you will add to it 6 mL up to, you have to have all your solution, they have 10 mL. The third one is you take 6 mL of your flask here, you will add to it 4 mL H2O. You take the last one is 8 mL more concentrated of your solution from the flask, you will add to it 2 mL. So all your solutions in the graduate cylinder, they have to be 10 mL. And then if you finish every test tube after I have 2 mL, I added 10. Take whatever you have, fill what? Fill your test tube number 1. Okay? Fill your test tube all the way to the top. You will not use the test tube, you will use part of the test tube, but fill it all the way to the top with how much you can carry on for out of this 10. Then you will do the second one. You will take the second one is 4 mL from the flask. You will add to it up to 10 mL, 6 mL distilled H2O. Dump it in the inside second one. The third one, 6 mL of the flask, concentrated one. You will add 4 mL of distilled H2O, transfer it in this. And the last one, you take 8 mL of the flask here, and then inside, then you add 2 mL of distilled, and then take this one here to 4. So you have 4 concentration, 4 different concentration. And looks at this. Here they are with the some 2 mL in the test tube number 1. This is test tube 1, 2, 4. That's on the flask here. flask into graduated cylinder, and this is H2O here in the graduate cylinder, this one in the graduate cylinder, in the graduate cylinder here. So this combination, then we can make a dilution law and then determine the concentration of this solution. For example, the first one, M1 V1 or C1 multiplied by V1. Some textbook put C1 V1. Instead of M molarity, put concentration. So they are the same thing. It's nothing different. So we have to determine the C2 or the M2. So you know that you started with 0.4. That's your stock from the stock flask there, correct? Volumetric flask has 0.4. You took 2 mL of it, and the total volume is 10. You calculate this one, C1 V1 equal C2 V2, or M1 V1 equal M2 V2. You calculate every time the molarity. So the molarity here, in this case here, is 0.8. The second, that's the first test tube. Second test tube is 0.116. Third one is 0.24, 0.32. Okay, so you have how many points? 4. And then you will add to it, 2 more points on the graph. So the graph will be, when we have at the end Excel, will have 4 points. The first point from us has to go through 0. You have to extrapolate your Excel to go through 0. When you make a table, make a 0. 0 absorbance means 0 concentration, correct? 0, 0. Then you will have, here is the absorbance. That's, you have to measure it. So you have 0.08. The second one here, 0.116. The third one is 0.32, and the fourth one maybe 0.32. So you have 4 points here, 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 here. So you have 4 points. So now we have 5 with the 0. Now you will have to have the stock solution itself. The stock solution without dilution. Remember, you took 7.3 grams. Dissolve it up to 100 mL of distilled H2O. So the 0.4 will come. This is 0.34, and here somewhere is 0.4 molar. So how many we have? So here it is. Let me write. This one is the concentration, 0.808, 0.16, 0.16.24. This one is 0.32, and this one, last one, is 0.4. So you have 6 points in Excel, and from there you have to determine the relationship. A equal constant, correct, multiplied by the concentration. Your constant here is your what? Slope, correct? And the slope is epsilon multiplied by L. You can measure the cell you have. We will not do that, but at least you can determine the epsilon. The molar absorptivity you can determine by experiment. So L is you can measure the cell, the path of the, the length of this cell. So how many centimeters is that? So then you can determine absorbance has no unit. So therefore the molar is mole per liter. Okay, and the length in centimeters. So your absorbance will have the units. You can see the absorbance. If you look at the absorbance here, will have a mole per liter concentration unit over the centimeter. Correct? Will be molarity over the length of the light path. Correct? So now from there, we did not finish. That's the calibration curve. This is what? Calibration curve. This calibration curve then we will do. You will. There is an unknown here. Don't open it in the cuvette. Ready to go, and it's covered with the plastic. Do not take the plastic apart. So you take out of the cuvette. Is already ready to go. Just you CHEM wipe the side where the light will go through. The light will go through. CHEM wipe it and put it in, and see where is its absorbance. suppose its absorbance came to be whatever, somewhere here, correct, or somewhere here. So let's have this one goes up. Suppose it came somewhere here, absorbance. That's what you measured of this. So from here, I would come to the line, correct? Going down, I can determine what? I can determine the molarity of my unknown. Everybody's following? So we have four calibration dilution we made with the 0, and with the start solution 6 points. And then we'll do the unknown at the end, all the way at the end. Put it in and see what absorbance this will give you from the computer. Your record, your computer, that will be whatever absorbance. You are not interested in the concentration. Then you hit, your concentration will come from the graph itself, from Excel. Everybody is following? Makes sense? It's very simple. It will not take 30 minutes, the whole thing. It's not really difficult. We will do 2 trials, because what you will do, just put it in, CHEM wipe it, put it back in. Are you following me here? You'll make 2 readings. And then every time what you will have from the program here, you have, I'm not going through the details in the program, so you can look at the details of the programs here. So the programs is here, Logger Pro. You'll turn it on, or we kept it for 15-20 minutes now, I think. So what you will do here, just follow this, the whole thing here, and make sure that the light is not going through the groove side. See this one here, there's the grooves. Can you see the grooves here side? Can you see them? There's a groove there. No, the light has to come from here. Oops, sorry, from here. This way here, going the other way. So there's very nice transparent face of this cuvette, of this cell. Are you following me? Not the side. This side always use it to grab this cell. That's the reason we make the groove, so you can always grab this from both sides. So you'll fill it first with the calibration with your H2O. Has to be the calibration. You have to calibrate it with H2O, distilled H2O, correct? Can I use tab water here? Yes or no? No, I can't. I cannot. I have some ions inside the H2O, might interfere with my absorbance. So you just follow those steps as very straightforward steps here. So every time after a calibration with H2O, what you will do here, you will have your scratch paper on your scratch paper, whatever. You have always the table here. First we did the calibration, correct? Then you will have to determine the maximum wavelength. That's this solution, nickel nitrate, nickel 2 nitrate, hexahydrate. What's maximum wavelength it can be absorbing light? What's the maximum optimum one? So you have to do first to get after the calibration. Calibration is telling you, are telling the spectrophotometer for the software, telling the software there, this is my starting point, where my 0. Remember the whole thing here, starting where? This is my 0. So the computer then, wherever is starting measuring the absorbance, and here you have your concentration. We will not give you the concentration. We calculated the concentration. We'll make a table for this, but you will have to determine what's best optimum optimum wavelength that this solution can absorbing light. You will determine here the software, and then you will make yourself a table. Those concentration you have, this absorbance, this is the concentration. So you have those concentration already, 0.8, 0.16, 0.124, 0.32, 0.4. I forgot one. Somebody will tell me. I forgot one. Which one I forgot? Somebody will tell me. I forgot 1 point. Which one? Correct. I forgot 0, 0. Correct. You start with the origin. So this is the absorbance. This is the molarity here, concentration. When you plot those here, you need the experiment to determine the absorbance, nothing more. You record the absorbance here, and then you have the table, whatever, 0.08 solution I made. What's the absorbance of it? and so on. So you measure the absorbance, and then you will do Excel starting from 0 to whatever is 0.4. So that's your Excel, whatever the absorbance is. The higher the concentration, the higher absorbance. Remember, direct proportional. The higher this, the higher of the concentration. So you can expect the last value of 0.4 will be the highest value. Okay, guys? Any question you have? I'm not going in details of how to do the software. Software is straightforward. Just follow it. Can we start? Promise me? Okay. So I'll stop now recording.